happy to have this before lunch, or you might be. So it is a technical deep dive, and it's the effort to have a new concurrency control model for NSO that will be introduced in 6.0. And it isn't like we haven't had efforts of performance and looking at throughput for NSO. That has been something ongoing for all time, I would say, that NSO has been here. But this is a new stab at it. And for that, there is a specific project that was done, and we are the blobs. So we needed new pictures, and they didn't never arrive. So, but you see the other guys, Viktoria, Fordos, Claes, Nasten, and Martin Åkerström. So if there is someone you want to ask something on this, you can pick anyone. So let's introduce some terminology. We might or might not need it. One thing that is important is to differentiate throughput from response time. So when you are a user and do a request, the time it takes for you for that response, that's the response time. And that's the first thing you see in performance. And it might be very annoying if it takes a long time. We are not very much bothered with that here, because what we need to fix or improve is the throughput, the amount of transactions that an NSO node can do in a given amount of time. And that has been lacking for a while. And what do you need to do to regard that? What is happening here? You need to have some sort of parallelism. And the concurrency control model, the concurrency control, is what is important. So you have all sorts of concurrency controls. You could have pessimistic, optimistic, some sort of locking, trying to be without locks. Anyhow, all of them will eventually end up in, if you're parallel, you might be in conflict with other transactions. So the conflict detection and the conflict resolving is an important part of this. Also, if you're in parallel, you need to think about the transaction isolation. And that isn't as easy as you first think, that I'm by myself, I read everything and it's okay. If there are parallel transactions, you have to decide, should I see what other transaction has committed or not? So this is something that is always discussed in DBMS systems, and we will have to think about it too. NSO have been here for a while, and normally the presentation on NSO is this picture. This is a very old one. It might have changed a bit, but anyhow, the important part here is that the service manager with fastmap and services, and the device manager controlling the device through NEDs is always part of these pictures, and also the CDB. And the thing is that CDB is not the database management system. It's a persistent store of config. And there is actually another part necessary for the concurrency control. And this is a transaction manager that is also shared with another product, confd. It's the same, or has been the same. So a white box view of NSO would be to pinpoint the transaction engine or transaction manager. And that is the one that is run when you start the transaction, when you go through the service invocations, when you go to the device manager and talk to the NEDs. And this is done in a two-phase commit manner. So to be correct, if you are in parallel, you need to have some sort of concurrency control, and that is what this transaction manager has also. But it does it by guarding the part which is necessary to be consistent in a lock. And this is something that you might have seen already, depending on how much transactions you try to run through NSO. So this lock becomes a hotspot, a contention. And this is why. So let's see. Yeah. This is the life cycle of a transaction. This part outside of this box, this is where you start a new transaction and you are working with that. So this is the work phase. This is the phase that we all believe is the transaction only phase, the one where you read stuff, you write stuff, you take decision, and then at some point you say, I want to commit this, I want to store it. And that is the apply phase. And there is all sorts of things going on then. First of all, there is a validation of all the parts that has been introduced in the work phase, and it's also the invocation of all the services that that transaction touches. Then there is a global validation of everything, the things that also was part of the service invocation. And after validation, it is a prepare phase, which has the kicker evaluations and also possibly other database callbacks, normally not used in NSO, but they exist. And of course, all the device manager part for both prepare and commit phase. And then when the commit phase is done, it's not done either then, because at the end, there is a kicker invocation. The kicker invocations are fast because the kickers are then executed asynchronously afterwards. But if you have CDB subscribers, they are part of the transaction until the time you say done. So that you can hold the transaction by your own subscription code. Okay, so the new way of regarding things, having a new concurrency model, the necessity is to scale, and scale on CPU is the most important part here. So the thing that is a problem is that, as you saw, there were a couple of red all these red boxes. This is where the programmer or user are allowed in to do stuff which affects the performance or affects the time spent. So that can be obviously in service code, but much of it is also in Yang as must expressions, when expressions, all these type of validated parts, in kickers, because it's export expressions. And all this makes it very hard to control the critical section. We do optimizations of all this all the time, but it's always for a specific use case, and other use cases, then it doesn't matter. So, one of the things that was introduced almost immediately in NSO was commit queues, and that is to move out the part that communicates with devices from the critical section. So we don't have that as a contention. And you know all of that. It's something that it is complicated, but it improves performance. What we now have done is that we have moved out almost all the parts that consume time outside of the critical section. So this is now run in Jeopardy. It's not everything, so there will be more to do in future versions. But this is where we stand at the point. And the big difference is that in the work phase, which is this part still, we need to collect the read set. We need to collect everything that goes through the transaction, not only what is written, but also what is read. Because we need, since this is all in jeopardy, the part that is here, we need a new conflict resolving. We need to see if anything that you read has been updated by someone else before you enter the critical section. And in that case, you need to abort. So that is the big thing here. There is now a read set, write set, conflict detection. So the read set of the transaction that I have, that I'm now about to commit, needs to be verified by all the transaction that was started after me and committed, or committed after me, so that I know if I read the right things and know that I took the right decisions in my transaction. So this sounds like a big deal, and it is, because you can expect transaction to abort with a new error code that says this was a conflict with another transaction. The good thing here is that we have pretty good control over much of these reads. The services, they can be restarted. That is what we do with redeploys, for instance. And validation can also be restarted. All these parts is something that we can control and help. So we actually have a service scheduling mechanism, and this picture is good because it's real. It was the first discussion about how we would restart services. And the big idea here is that you can have conflicting services that are just ad hoc. This was once in a while. And then it's just a restart and everything works. No one has to bother. But it might also be that a certain service type conflict with itself. This is by design. And in that case, this scheme with restarting doesn't really hold. So what you need to do then is to identify that this service type, this service point, conflicts all the time and go back to the old view. It can't be run in optimistic fashion. It needs to be serialized. And that is also done automatically. And you can get information about that. So if you have that, you can either decide that this is good enough, or you could revisit the implementation and see, is there anything I can do so I can get rid of these conflicts to improve performance? Yeah, this fun picture is a way of saying the same thing. All these guys are supposedly transactions. In the outer rim, it's newly started transaction in a work phase. These guys are reading stuff, taking decisions, writing on top of that. And then at some point, the transaction is going into commit. And this first inner circle is that. And at that point, we do the validations and the service invocations, and we tag these parts of the reads, these parts of the writes as separate, coming from a service or validation phase. And one at a time, the transactions can enter the critical section, the part where you need to store, persist the data. And then the transaction that is running at the point, it verifies all the transactions that has been done after I started. Do I conflict with them? And if I conflict in a part that is after the work part, which is from the service or validation, I can just restart and do this in a loop. But if I abort because of things that was read in the work phase, that was actually the original user that read, and the decisions that was made out of that, we don't know. We don't even know if the reads was necessary or not. So these transactions need to abort. And if it's okay, then this transaction it's a manhole in the middle. So the transactions eventually want to jump in the hole. That's the idea here. Yeah, so this is basically how it works.
Yes. So let's talk about a few of the obstacles and opportunities we had when doing this. Changing the core architecture comes with unexpected risks. There is a lot of less optimal design choices taken in the past that you will have to find and fix. And fixing 4 out of 5 of these doesn't necessarily mean that you will gain anything. So it has been a long journey getting where we want to be. But changing the core architecture also comes with unexpected gains. Opportunities will present themselves when scrutinizing the details of the system like we have. And opportunities that we haven't been able to do before. So let's look at some functional highlights for NSO 6.0. So first of all, we have lockless dry run. This is one of the most important features in the product for the user to verify that the transaction does what the user intends. And there's a lot of customers that use this in an automated fashion. So previously, this was done inside of the critical section as the validation and service invocation had to be done there. But by moving these, we can also move dry run. And by making dry run lockless, we will reduce the overall time spent inside of the critical section, as well as making response times faster. We don't need to wait anymore for other transactions to perform a dry run. So that's great. We also have parallel execution of commit queue items with NSO nodes. So this is a key feature to give throughput in a clustered environment. The collected read set will be used to detect read-write conflicts on queue items ahead of it. And if there are no conflicts, these queue items can be run concurrently. And if there are conflicts, we can just paste them as we have done previously. Next on the list is improved device locking. So since service invocation was previously done within the critical section, we couldn't determine what devices would be part of the final change set. So the device locks had to be acquired within the critical section, and if they couldn't be acquired right away, we would have to abort the transaction. Now we can take these automatically before entering the critical section and wait until these became available to us. So this will simplify both user code and operations. And by running more parts outside of the critical section, we can now start thinking of trading response time against other benefits without affecting throughput that much. So by enabling compression on service reverse diff sets, we can now trade response time against reduced memory growth and a smaller CDB. But thanks to the changes we made for NSO 6.0, we also been given opportunities to improve the system on previous versions. So let's mention a few of these highlights that we already released and that we were able to do due to the work that we had to do for 6.0. First of all, we have improved commit queue error recovery. By changing the internal service metadata handling, this was necessary for 6.0, we were able to improve the commit queue error recovery by enabling it also for RFM services and non-services. We also have internal performance improvements for CDB, making internal data structures becoming more efficient. And by doing this, providing an overall performance improvement in the system. Also have internal performance improvements for kicker revelation, reducing the time spent inside of the critical section. And as you previously saw, this remains within the critical section right now, at least. So, where are we now? Let's talk about some numbers, what we have achieved in terms of throughput by making these changes. But first, some expectations. By making these changes, we expect better CPU utilization, making use of as much cores as possible. We also expect improved throughput, more transactions pushed through the system within any given time, and we expect minimal memory increase. In terms of functional expectations, we expect minimal or zero code change to get this benefit. This will, of course, be dependent on the customer, how they have written their services. We also expect minimal impact or no impact on CDB. We don't want an expensive migration experience for our customers. Also expect minimal API changes and most of the user code running outside of the critical section. But now for some actual numbers, what you've all been waiting for.
Yeah, so on the last page, let's revisit it another way. So to verify that we actually can do this on existing deployments, we need to have the existing deployments to test on. Because one first idea might be you must be on drugs trying to do this. So that's what we have been doing. We have tested a couple of real use cases from the world outside the office. And the first one here is a LSA implementation. It actually has one CFS node and two RFS nodes. We are just measuring the one that paces the system. It's the one that uses NFO. And it's actually a bad one because the CFS services uses one service from the NFO node and one from the other, and the other conflicts by design. So this is one where you can't really be parallel all the time. But anyhow, and also we are testing this on very big machines, or at least in my point of view, big machines. It's a 72 core machine with 1.5 terabyte of RAM. We don't want to be measuring the machine in the workings. We just want to measure NSO and NFO behavior. And the blue one is the 5.7 approach running this. And it is a bit of ups and downs, but it's more or less like on this machine, 3 processes running 100%. So it's completely saturated by trying to do services. And with the coming 6.0 pre-released version, we see that there is a big peak, and that one comes from the part which is NFO, which have at least 3 times improved performance. So that converges all its services is in a third of the time as before. And then there is a long time since the services conflict, they will be detected and run in sequence. But still, there is a performance gain. So that was fun to see. Next case is a TSDN service pack case, which runs on the same machine. I think it's one service addresses 4 devices at a time with a reasonable payload. And the gain isn't really as much as the other one, but at least 2 times or a little bit more than that. Next use case, and also these 2 previous ones are nano services. So they need time to converge. They cost more because it's more transactions involved. This one is an LSA with 2 nodes, one CFS and one RFS, which have normal services, very small, very fast services. So if you think about all the different boxes that we have moved out of the critical section, if they don't take any time, you are not supposed to find that much difference between the old and the new solution. But then the mentioning of LSA and the parallelism in the commit queue in LSA, that makes all the difference. So you get a 3-time improvement, and that is because the whole system becomes parallel in a new way. Okay, so I also can present some of the things that has been done in San Jose on a more massive scale testing that is on the courtesy of Anshu Narang. And for further details on that, I think you need to be in contact with him. But it is another version, a newer version of NFO in the first case. And the setup is on a more reasonable machine, 8 CPUs, 32 gigs, and not that much disk. The idea is to run NFO on the Sol 3 system with mock-up ESCs, 2 of them. And they are set to, it's a 5-minute wait to converge on these ESCs. So one service takes 5 minutes at least to converge. And with tested on 10,000 services in a go, in a single thread, which doesn't matter in the old system, because if you just run more, you just perform more work, but it won't go faster. So that takes 14 hours, 36 minutes to converge 10,000 services. And yeah, it's a certain amount of memory used and stuff like that. So it's compared to the pre-6.0 release on a single thread. Single thread means that you start all the services one after each other and wait for the commit. So the commit time is 2 seconds. So you wait 2 seconds, then you can do the next one, and then you can do the next one. So the parallelism of this is just because it's a nano service. There's a lot of redeploys going on. But the convergence is also here, roughly 3 times. And it's also tested when you start to do more in parallel from the beginning. And there isn't much of a gain here. So the sweet spot is probably around 1 or 2 threads. And the thing that you see here is that the commit time starts to grow. And this is not astonishing. It's a problem with optimistic transactions, that when you have a lot to do, there becomes a lot of conflict resolving. And this is actually things that we will, and we are focusing on right now, There are more than one way to look at that and do more, but this is the figures that we have today. The other use case is TSDN, slightly bigger machine, but still reasonable. Running TSDN on iOS XR NetSIMs, and it's a setup with 300 NetSIMs, and the services are round robin, so they are four devices in one service, then next four, then next four, and then after 75 services, it's back again to the first one. And also here we have good improvements, and yeah, that's something learned in doing this work. The intuition never works. Every use case is different. So it's a good thing, first of all, that these use cases work out of the box. There is no migration of CDB, there is no changes in the code. But they all give roughly the same performance gain. Oh, sorry. From 18 hours to 11 hours on a single thread, and with 5 threads. Here the sweet spot is also somewhere between single thread and a couple of threads, because you can see also in this case, 17 seconds on commit, we are starting to do more and more work on conflict resolving. So this is certainly something that we will work more on. But anyhow, still good results. What you might see is that the response time grow. So that's an annoyance, but still for us it's the main idea to do as much throughput as possible. So this was more or less it. There is another presentation by Viktoria and Claes on Thursday, which is a deeper deep dive. But I think that the general idea is to regard what you could look at to make this work even better. We said that it should work out of the box, but if you regard what we have, you can do much more to improve. Okay.
Thank you, guys. Do we have any questions from the audience? Yeah, I see one below there. Yeah, wait for the microphone.
Oh. No, you don't have the mic on.
So if I understood correctly, the kicker evaluations are still done in the critical section, or
The kicker evaluations?
Yes.
Yes.
Yeah.
Yeah, so we had to stop at some point. You could go on optimizing all the time, and we will, but at this point, we wait with that, because they are a bit tricky to move out, but it's certainly doable. It will just be more work. So hopefully, and also for some use cases, that will be a gain. If you don't use kickers at all, you won't see a difference at all.
All right, thank you.
Yeah, a microphone down here, please.
Yep. I had the same question.
Oh.
I'm here. Yeah. I had the same question actually, but what I understood that I believe the kicker will not be triggered until the conflict algorithm have been already finished, right? If I have a service that have been committed, the kickers will not work until the conflict have been resolved or have been checked at least, right?
Yeah, exactly. So since the kickers are in the critical section, these are transactions that are actually committed. Then that is like before. It's certain that it should be kicked, it will be stored.
Okay.
And that's the thing.
Yep.
If we move them out, we need to create a read set for the kickers, and we need to be able to abort based on the kicker reads being in jeopardy instead.
Clear. The second question that I had is, do we have any benchmarking, like, for example, the maximum number of transactions that can be done concurrently based on the resources that we have?
No, I know people that say that they can do pretty much the figures they want, but I'm not sure. There are, that's not true. But we have been so focused on real deployments that they should work out of the box and should gain something, that the first time we have thought about it is the presentation that is on Thursday. What you should think about to be as smooth as possible. And there are still a lot of things done in the critical section. So I think that what we will have to measure, but there will be a struggle and an urge to do more later on. But this first part, making this an optimistic transaction, that was necessary. Then we can optimize. So
Clear.
hopefully all the changes that are a nuisance will be done in 6.0, and then it will only be gain.
Okay, thank you.
Hi, thank you. Regarding the CDB, you said you did some improvements on the data structure. That meaning migrating from 5 dot something to 6, is there anything that you're forecasting and any extra work you need to do?
No, I mean, the compression service reverse diff sets, that is lazily performed. So when you redeploy your service, then we will compress it for the first time. So you will not get a smaller CDB the first time you start up with 6.0, but you will eventually get there.
Yeah, and I perceive this presentation to be much more fun and lazy than it became. And one thing that I didn't remember to say is that the CDB on disk actually reduced in a lot of these use cases, and that is because of this compression. So you could perceive memory to be used more because you have more transactions going on at the same time, and it will happen. But there is also less memory because of the compressions that are going on.
I mean, the two major parts that take up growth in CDB is device config and service instances. And by enabling compression on service reverse diff, we have seen roughly 10 times compression rate on the service part. So, but that's not a real. I haven't seen this in a real customer environment. This is.
But you have a gain.
But I have a gain, and I've seen this in like local tests. Yeah.
Yes, and do you foresee any benefits for actions such as deep check sync or compare config, especially in LSI mode?
I mean, not in deep check sync, I guess. I mean, all actions that use dry run will gain for sure, since you will not enter the critical section at all. So yes, I think there will be gains there as well.
On service check syncs, but on device check syncs, they are not used.
Not device check syncs.
No, because they are not
service check
using,
syncs. Deep, yeah.
Sorry. Early on in the presentation, you mentioned that some of the device communications being moved out of the lock area. Does that mean that we're having more network noise from NSO to devices that we need to account for? Is there a bigger load on the network?
No, I think that the thing I meant to say was that the commit queue, which has been there all the time, has been a way of moving out that part of the transaction from the critical section. We haven't moved anything else. The thing that you refer to is in the beginning of the transaction, before we enter the critical section, we know now everything that will happen. We didn't do that before. Since we have run the service invocations, we We actually know exactly which devices will be touched. And that is a big difference internally for us. But that's on the forefront of the critical section that we can do stuff. And that's important.
Exactly.
I don't think we have moved anything else from the device manager out.
No, we haven't.
Okay, I think we should break here. And of course, you can approach the guys and ask any question you like during the day. So with that, thank you.